Hello, everyone. Cheers, and welcome to tonight's edition of Astronomy on Tap. My name is Laurent, and with Jake, I'm hosting this event. Jake is going to present the pub quiz later. For those who don't know, the event is going to go as follows. First, we will discuss a few news related to astrophysics. After that, we will have a great talk by our speaker of tonight, during which you can ask questions on all social media, YouTube, Facebook, Twitter. And I will ask the questions to our speaker. And we will then all go to the Zoom pub for a nice pub quiz. And after that, we can all share a nice beer and talk and have fun together. So without further ado, tonight's speaker is Stefi Baum from the University of Manitoba. Stefi?
Okay.
Hello.
Hello.
How are you doing?
I'm good, thank you.
Ready for tonight?
We'll see.
And together with us is Katja Frontseva for the discussion on the news. Hi, Katja.
Hi, good evening.
Hello, good evening. So we can jump on the news right away. The first one is a bit more technical than what we're used to. We've discovered recently, so scientists have discovered recently, a lot of OB stars in our Milky Way. And OB stars are actually very, very massive stars. And as they're massive, they're very bright and actually very hot. And since they're hot, they're blue, because actually blue is hotter than red in space and in physics in general. And what's interesting about them is they're very rare, because they have a very short life, which is about 5 to 6 million years. Which is, okay, long, but not at the cosmological scale. And here they are a bit above the plane of the Milky Way. So they might be they might show some collision with a previous galaxy. So that's what they found. So Stefi, did you work with big stars like that? Did you work on big stars like that?
Well, I study big stars like that in external galaxies, where they can, again, similarly be a sign of some sort of recent interaction or activity. So same idea, something, it's a spotlight on something that happened relatively recently in terms of cosmological time.
Yeah, that's so yeah, stay tuned for more information on that. The second news is actually New Horizons, which reached a milestone in space. So it was launched in 2006 and is now 50 AU. So an AU is the distance between the Earth and the Sun, and is now 50 AU from us. And so it's only the fifth spacecraft to have done that, after Voyager 1 and 2 and Pioneer 10 and 11. We talked about Pioneer last month. And before, it was like, when it was launched, it would take only a few minutes to get a message to New Horizons, but now it takes actually 7 hours to send a message. Minutes to get the message. And that means 14 hours to send a message and then get the confirmation back that we got the message there. So it's quite crazy. And just as a bit of information, it was sent to study Pluto and also some object in the Kuiper belt. So this is quite an accomplishment.
I have to say, actually, that it was launched to study Pluto. And then, because the way how the mission works is that you just, you launch it, and then, well, you don't really do any flight corrections. It's basically just, let's say, goes on its own. Then after the New Horizons passed Pluto, the team of New Horizons worked very hard to look for any other object that New Horizons will pass by later. And so they found this Kuiper belt object that is now called Arafat, I think. So this was a second target that New Horizons flew by. And I think the plans of the team is that They are trying to find more Kuiper Belt objects that can be on the way of New Horizon spacecraft. And I think it's really cool because the mission was launched in 2006, right? Yes.
Yes, it was.
Yeah. And now it's 2021. I'm always having hard time with years. And I read that if everything goes smoothly, then there should be enough power to to have communication and also to perform science on the New Horizons until late 2030s. So it's around 15 years more. That's really a lot. I think it's really impressive. And so if they find another suitable Kuiper Belt object that will be on the way of New Horizons, that will be very, very interesting to see.
And so that was not the plan at the beginning.
Well,
just
I
adjusted
think,
it?
No, I think that when the mission is designed, of course, it's discussed that if everything goes smooth and the primary science target is achieved, then there are always secondary scientific targets that are discussed, but I think they're always, they're not defined 100%. So I think maybe we can ask also Stefi more about it.
I'm not an expert on this one, but I think that there have actually been multiple, I think, NASA planetary missions that have found a secondary purpose after they carried out their first one. So I think now when they're making missions, they know that that's a likely outcome. And so though it's not one of the primary requirements for success, I think they're starting to plan more and more. Why not keep getting science and learn new things once you've made the initial investment? So it's very exciting. Yeah.
It's good in the recycling idea that we have.
It's a green mission.
On to the third news. Stefi, I don't know if you followed it very thoroughly, but for the past 2 months now, we've been talking about Ingenuity, the helicopter on Mars, which 2 months ago we said it will be flying. And then last month we said it will be flying very soon. And actually it did it now.
4 times, right? 4 or 5
times? 4 times, indeed.
4 times.
It flew one time first on the 19th for 3 meters for like 10 seconds, for 30 seconds, sorry, above the ground. And everything went really well. So you can actually watch a video on the internet from the rover who made a video of Ingenuity flying. And there's a picture of Ingenuity taking the picture of its shadow. So that's really cool. It doesn't look very impressive, I have to say, but it's actually super, super cool. And actually the chief engineer in charge of Ingenuity, they already say that it's a good thing that they managed to do that. It's going to open the way. And they're already sketching, let's say, a second helicopter that could, that would be 10 times more massive and could carry like scientific load. So that's really cool.
Very cool.
And yeah, already 4 times. So they took their time to do the first flight, but then they were like, okay, let's do as many as we can.
Do you know if there are any plans for more?
I think there is now. I thought I was reading that there might be a 5th flight. I think they've already surpassed their, milestones, their requirements for how far they're going to fly and how long they're going to be able to fly. So I think I saw somewhere they might be planning a fifth flight. So
yeah, I think the idea was already to fly once, because I read that the helicopter flies autonomously, so it's not controlled, and actually they need a probe around Mars to recover the data, and so they only got the data of the flight 3 hours after the flight, so they had to wait. So that must be really so
frustrating.
frustrating to be like 3 hours of knowing if like people have been working on it for a while, I'm guessing, and so if your work managed to work. So yeah, so that will be probably the last piece on Ingenuity in this show. And now on to the last news. The Hubble Space Telescope is 31 years old now. It was last month, And yay! And just so a few news, it was launched in 1990, and it was initially designed for 15 years, about 15 years to work. And actually it's still working now. And I've read that it's going to be working maybe even 10 years more with JWST. So the James Webb Space Telescope is going to be launched soon, hopefully. Uh, and yeah, among the accomplishment, it managed to determine the rate of expansion of the universe, to confirm black holes inside of galaxies, and also to take a lot of beautiful pictures that you might have seen on the internet. And actually, Steffi, you've been working on the HST, right? On the pipeline.
Yeah, it makes me feel very old when I hear it's been working for 31 years, because yeah, I went to work there shortly after I got my PhD and had finished my postdoc. So yeah, I worked there for about 12 years. And actually, Jake, when he was a graduate student, was working with me when I was at a Space Telescope. So he was there as well. So yeah.
And what do you think? What's your favorite thing about the telescope? Do you?
So, I mean, my favorite thing about the telescope was actually the first Hubble Deep Field, when Bob Williamson, the director, and a bunch of scientists got together and planned to take the deepest image, just have the telescopes stare at one place for a very long time and see what was out there. And that was very illuminating in terms of what we know about the early universe, but also it basically fundamentally changed how science was done in astronomy. So sometimes the biggest accomplishment is not just the technology, but also the changes in approaches to science that result from it.
Yeah, that's the HST really, revolutionized everything.
Yeah.
Yeah, so that's it for the news. Ciao, Katia.
Okay, bye-bye.
Bye-bye. And
Ooh.
you can tell us all about black holes and galaxy evolution.
Okay, we shall try. So let's see. I'm going to, what do I do first? I go into play mode.
If you can share screen.
Uh-oh. 1 second. I have to Command Tab. Okay, there, we're back. And then share screen, desktop, share. Did that work?
Yeah, it's perfect.
Okay.
It's
like patting your head and rubbing your stomach at the same time. So hopefully this will work. So I'll just start. So my talk title is The Never-Ending Story of Black Holes and Galaxy Evolution. And it's never ending because we have so much to learn. And every time we think we understand something, we learn that we don't quite yet. And for me, it's a great adventure, such as the never-ending story. Now, let's see if I can get this to work. Okay, so the image here that you see, I don't know if you can see my, is a galaxy in the green. That's the light in the optical part of the spectrum, and the green shows you where all the stars are. In the red, you see these enormous jets and plumes of material issuing forth from the very nucleus of that galaxy. And those are cosmic rays spinning in magnetic fields and pouring energy out from what we believe is a black hole in the center of the galaxy. So this talk is going to be about the relationship between the black hole, the jets, and the galaxies, and why that provides us with interesting conundrums to understand. So first, we'll talk just a little bit about galaxies. Galaxies are large systems of stars and interstellar matter, consisting of from several million to some trillion stars, individual stars. And this is just a montage of different galaxies. They come in a wide variety of shapes and sizes, and they typically have not only stars and gas, but also dust. And that's the sort of obscuring material you see that blocks the background light. So in a universe far, far away, long, long ago, there was something we don't quite know, Big Bang, physics started. And over the course of time, particles came out of the ether, so to speak, out of the void and formed into atoms. And then eventually they formed, as they cooled and coalesced, they formed into stars. And then the stars started to evolve and liberate electrons and have explosions. And as time went on, then galaxies started to form. And here you can see a timeline since the Big Bang. And sometime around 1 billion years ago or earlier, we started to get reasonably numbers of galaxies, and on into about 3 billion years ago, when all of the activity from the stars and black holes started to reheat the intergalactic gas, clusters of galaxies formed, and here we are today. So just as a note, we think of this process of star and galaxy formation, it went on and it produced our galaxy, but it wasn't actually very efficient. It's a very inefficient process. And all the things we see here glowing in the light that our eyes sensitive to actually constitute a very tiny fraction of the matter and energy in the universe. So when we look out into space at stars and galaxies, we are seeing only 1% of the mass and energy. Okay, so what's a black hole? Black holes can have masses which are anywhere from several times the mass of the sun and on up. And they can be as large as 1 million to 10 to the 9th or 10 to the 10th solar masses. And this is just an artist's drawing of a black hole named Cygnus X1 that lives in our galaxy, formed when a large star caved in. And the black hole, which is in the center, is believed to be pulling in matter from an orbiting blue star with a big envelope. And as that matter swirls in, eventually at some point it reaches the event horizon and falls into the black hole. And out of the black hole, or near the black hole, are issuing these jets of matter, similar to what you're going to see in the large-scale radio galaxies. So black holes are the evolutionary endpoints of stars that are, say, 10 times or more massive as the sun. And if that star undergoes a supernova explosion, it may leave behind a fairly massive stellar remnant of around 3 solar masses. And what happens is the gravitational pull of that matter outweighs any other forces left in the dead inner part of the star. And so it can't sustain its size, and the remnant collapses. And eventually the star will collapse to the point of 0 volume and infinite density, creating a black hole. Basically, it becomes denser and denser because there's no force to withstand that. It's also believed that there might be micro black holes that formed in a different mechanism in the early universe from the pressure of the surroundings. So we know that type 2 supernova often leave behind, or sometimes leave a black hole behind with 10 solar masses, sometimes a few tens of solar masses, and we've observed those. But in the centers of galaxies, in the nuclei of galaxies, we have black holes which are millions to billions of solar masses. So how did we get those very massive black holes in the center of galaxies? We don't really know. One possibility is that early universe, there was a merger of many smaller black holes to build up the massive ones. If that process was going on, we might think we would be able to observe intermediate black hole masses of 100 to 1,000 solar masses as part of the building blocks. But it turns out that these seem hard to find in one of the continuous conundrums of science. And a recent study showed that a dark mass of 1,000 solar masses in the center of a globular cluster, which people thought might be one of these intermediate mass black hole, is not actually an intermediate mass black hole at all, but is a cluster of very compact objects, including white dwarfs, neutron stars, and black holes. So not everything is a black hole, even things that you think might be, and many things remain, of course, not understood. Now, we believe that the black holes, both those in stellar systems, but also those at the center of galaxies and the nuclei of galaxies, can affect their environments with quote unquote light and fury, signifying that in the galaxy there's an active galactic nucleus. And this is just two artist renditions. So let's learn a little bit about the active nuclei of galaxies. This is the standard model of the active galaxy nuclei. Here in the very center is the black hole. It's surrounded by an accretion disk on the small scale. And from that disk is heated to high temperatures and emits lots of optical UV, X-ray, and infrared light. And in addition, by some mechanism poorly understood, a jet is accelerated that comes out of that nuclei, and in radio galaxies can extend for many, many times the size of the galaxy. Around that is some kind of obscuring torus made of dust and molecular gas. And we now know that frequently there's actually quite a bit of outflowing gas associated with that molecular torus in a broad wind. So this torus that we saw that surrounds the accretion disk in the black hole is actually, as I said, a very dynamic structure. And a lot of, you can see in this graphic that there's a lot of cold molecular gas that is flowing out from that structure. So the fury from the black hole is the mechanical energy that comes out from this outflowing radioluminous plasma. And you can see these very, very luminous jets in which the material is actually flowing out near the speed of light. And that goes, see, this is the size of the host galaxy. And you can see this stretches many, many times the size of the galaxy way out into what's called the intergalactic or intercluster medium. And that then inflates these giant lobes and with the various shock patterns in that medium. And the radio sources can dissipate a large amount of energy in this intercluster medium. And though that energy can trigger star formation, like we saw in those OB stars, which we heard about in the news. And the radio sources can snowplow the ambient gas, creating big arcs and bubbles like you see in this radio image of M87. When you look at low frequency, you can see all the large scale and older gas that's been flowing out from the black hole in the center over a long period of time. So a lot of energy is put out into the medium beyond the black hole as they drive these shocks and sound waves in the ICM. And this is just X-ray image of that same M87 area, black hole, radio source in green. And these are the X-rays. And you can see the shock waves that are being driven out into the medium from this expanding radio source. So how are we going to get these large scale radio jets, which have such an impact on their environment? So you need a black hole. You need some kind of accretion disk from which matter can flow and fuel the black hole and create the source of energy, which is gravitational energy, to get everything going. And then you need a supply of gas for that accretion to happen, as well as magnetic fields. And it turns out most likely the black hole has to be rotating to spin up the radio jet. So this will become important later when we talk about the association of black holes and energy activity in the center of galaxies and the evolution of the galaxies. In the centers of these clusters of galaxies, which are many, many galaxies which live together in space, hundreds to thousands of galaxies all in the same area. And the centers of those are occupied by giant ellipticals. And one model for these is that they grow by interacting with and gobbling up smaller nearby galaxies. And this particular one has many different galaxies in it, and then a huge diffuse envelope. And the supermassive black holes, therefore, in this central galaxy also grow to greater accretion and coalescence with other black holes. And these giant ellipticals often have active galactic nuclei and produce these giant radio sources. Okay, so how do we know, or why do we think that black holes are actually real? Well, the best example is probably our Milky Way galaxy, which we believe has a couple million solar mass black hole in the center. And this our understanding of this is an old image, but now that these paths have been, tracked for all the way to 2020. And the way they was determined is they watched the path of individual stars circling around the center of the galaxy. And then they can use that information to calculate what the enclosed mass is that is keeping those stars bound and on those orbital paths. And when they do that, they conclude that we have this large 10 to the 6, 10 to the 7th solar mass black hole in the middle of our galaxy. And we think we're a pretty common variety galaxy. And there are also another sign of that we may have a black hole in our galaxy. There are the two large Fermi bubbles of gamma detected in gamma and X-rays, high energy cosmic rays that tower well above. Here's the plane of our Milky Way galaxy where all the stars live. And here, towering way above that, are these giant plumes, space bubbles, and we believe those may be fueled by outflow of matter from the center of our galaxy from the black hole. Now, more recently, we've had the exciting results coming from LIGO, the interferometer, which detects gravitational waves, and using a laser to see the change in the metrology of two different systems spread across the US. And I'm going to show you a video from this, at least I'm going to try to. Sorry. And I think the best way to do that might be to find this. Here you go. I hope you can see that. This is a simulation of what LIGO observed when it detected the coalescence of two black holes that were in orbit around each other. These are stellar mass black holes, not supermassive black holes. And as those black holes rotate around each other, you can see that they're deforming the space-time around them and sending out waves, gravitational waves corresponding to those changes in space-time. And that's what LIGO was able to detect. Okay, let's see if I can get that away and go back. Oh, uh-oh. Sorry, what did I do? Let's see. From current slide. Okay, you're still there, good. Let's see if I can get this back up. Okay, great. So that detection, which was on announced in February of 2016, they're continuing to monitor, and as you may know, they have new detections all the time. So these are the first detections of gravitational waves, ripples in the shape of space. And
black holes are one of the strangest things in existence.
Okay,
they don't seem to make any sense at all. Where do they come from? And what happens if you fall into one?
Oh God, I'm trying to find it.
Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own sun, the heat and pressure at the core allow them to...
I'm not sure what this is. Sorry, I'm not sure what happened. Maybe that was just the next thing on that page. Okay, so the next way we know that that black holes exist is by observations of the supermassive black hole in the center of M87. And the image that you see here is actually taken with the Event Horizon Telescope, which is a giant interferometer, different radio telescopes spread across the Earth that are operating at millimeter wavelengths. And by combining the image from those different telescopes in interferometer mode, we can get very, very precise small scale image of the center of the M87 galaxy. And this image shows the bright ring formed around the black hole that as light bends in this very intense gravity around the black hole, and that black hole is 6.5 billion times more massive than our sun. Uh-oh, now what happened? Okay, so let's talk a little bit. I won't show that video because I'm not sure what's happening with my videos, but how are galaxy evolution and nuclear activity linked? That's what I told you at the beginning I would talk about a little bit. Oops, well, okay. So why might, let me just see what's happening here. I've slowed to a snail here. Okay, sorry. Okay, so why might we think that black holes actually affect galaxies and their environments? Why would their evolution be linked together? So here are a couple reasons, though there are others, but I'm just going to talk about two so I don't talk too long. The black hole masses in the center of galaxies are actually correlated with the total galaxy mass is one reason. And another is that there are too few really massive galaxies. And we think we may have an explanation for that in terms of the impact of the activity on the galaxy. So the first one that I talked about is the observation that there's a correlation between the black hole mass in the center of a galaxy and the mass of its bulge. Now, what is the bulge? Well, elliptical galaxy like this one is all bulge. So the galaxies that produce those giant radio plumes and jets are mostly elliptical galaxies, which are dominated by bulges. As you go down the sequence of galaxies, you get lenticular galaxies and then down to the spiral galaxies, which are dominated more by the spiral plane and less by the elliptical bulge. So what correlates in this mass is not the mass of the galaxy, but the mass of the bulge and the mass of the central black hole. So this is a little complicated, so I'll explain this. But this is one of the problems we have with understanding galaxy evolution is when we put in all the physics that we think exists in how galaxies evolve, we find we cannot. There are too few massive galaxies observed compared to what the models would predict. So the question is, how do we prevent massive galaxies from forming? So what you can see, this is the most massive galaxies and the smaller galaxies. And the dots are the actual observations. How many of each type of galaxy is there of each luminosity, how this brightness galaxy, how many galaxies are there? And this, what you see here in the dark line is the prediction in a case where you include heating by the central engine, by the active galactic nuclei impacting the galaxy evolution. And what you see in this dotted line here is with no contribution of energy coming out of the central black hole, the AGN contribution. And you can see that in that, without the central AGN, you predict many, many more big galaxies than you actually see in the universe. Now, remember, we talked a little bit previously about how these black holes and these big radio jets and these outflow of energy from the central engine might actually be impacting things in these galaxies. And this is another example. This is in 3C84 in the nearby Perseus cluster. And again, in the green here, you see the region where the radio observations show a jet and two lobes coming out of the radio source. And these are X-ray images, and you can see very clearly a whole series of shock waves in the interstellar and intercluster medium that we believe issues forth from the activity in the black hole. So the other query is, okay, so the black hole is not enough necessarily to predict what will happen in terms of luminosity versus the power in the radio. Remember, bigger galaxies tend to have bigger central black holes, and they also tend to be more radioluminous. So this is a plot of radioluminosity going up this way. These are the more radioluminous ones. And the luminosity of the host galaxy, i.e. how many stars are there in the host galaxy. So out here you have the most massive and the brightest galaxies, and down here you have the least massive and the less bright galaxies. And what you can see up is that clearly, as the chance of something having a large radio power producing this big outflow from the nucleus goes up quite dramatically with the size of the galaxy. But you can also see that they're not clustered around a little line. There's many orders of magnitude in dispersion in radio power for a given size of host galaxy. Some of that may be variability, the engine turning off and on, but we don't know what regulates the radio power. So galaxy stellar luminosity or black hole mass is clearly one critical parameter, but it's not the only one. And other ones are probably the rate at which matter is falling into the black hole, as well as the black hole spin. So to summarize this talk today, supermassive black holes, as well as stellar-sized black holes, appear to exist. The black holes release energy from their accretion disks of the form of radiation and powerful outflows, both in stellar systems, but also on massive scales in the galaxy system. And that energy seems to be responsible for the relationship between black hole mass and galaxy mass. It seems to be the cause of the limit on the mass of the largest galaxies, why we don't have as many large galaxies as we might have expected. And I didn't talk about it much today, but it's also responsible for heating of gas in the clusters of galaxies. And black hole mass matters, but clearly it is not the only important parameter. Accretion rate and spin matter too, as well as, I'm sure, many other things. So that's the end of my talk today. Thank you.
Thank you, Stefi, for this very interesting talk. It triggered a few questions from our viewers. The first one being, where does the torus surrounding the black hole come from?
Well, we don't really know, but we believe as stars and molecular clouds circle around the center of the galaxy, that if they can lose angular momentum, be perturbed in some way, either by the passage of other stars, molecular clouds, or interactions with nearby galaxies, then that matter can be torqued to fall in further into the central black hole. And as it does, it needs to shed its angular momentum. Some of it goes into the disk and some of it falls into the black hole.
So it's matter being accreted that kind of separates.
Yes, that's right.
Okay. Have we ever detected two supermassive black holes colliding?
Yeah, well, there's many observations where people think that two supermassive black holes are in orbit around each other. And I don't know that we've seen the gravitational signature yet from two black holes colliding per se, that we've been able to identify that way. But there are large energy events that people think may turn out to be supermassive black holes colliding, or a big black hole eating a smaller black hole.
So we might have seen it, but we're not sure yet.
Yeah.
Okay. When can we get an image of the black hole in our galaxy?
An image of the black hole in our galaxy. Well, that's a good question. And I should know the answer to that, but I don't know what that would look like. So Right now, in fact, the black hole in M87 is the only one that I showed you the Event Horizon Telescope image of, is the only one that has really been imaged. It's very close by, and it's a supermassive, very big black hole. So the Event Horizon Telescope is in the process of ramping itself up to get increased collecting area, more sensitive detectors. And so there's a version 2.0 planned of the Event Horizon Telescope, which fortunately, because it is just comprised of many different telescopes all around the world, can continuously upgrade itself. And so it has plans for higher resolution images of M87. And I don't know the answer about our galaxy, but it will be interesting to check. It's a sensitivity issue, right? That you have to have enough signal to observe.
The one in our galaxy.
Yeah.
Yeah. Okay. How do we know that black holes spin?
How do we know the black holes spin? Well, there's various diagnostics from emission lines, particularly in the X-ray, that broaden in a certain way, that are predicted to broaden in a certain way if the black hole is spinning. And so those observations have been made to suggest that various black holes are spinning.
Okay.
And it's also part of the theory of how you might be able to, what you might require to launch a jet would be magnetic lines that are tied to a spinning black hole.
Oh, so these two jets that you've seen,
yes,
that you've shown a couple of times. Okay. And last questions. Why do more massive galaxies have more massive black holes?
Yes, wouldn't it be nice to know that? So, you know, that's one of the things, again, you talked about James Webb Space Telescope, and we're excited for that. One of the things people can't understand is we keep seeing signs of supermassive black holes, such as quasars, earlier in the universe, where we wouldn't have thought that the black holes had time to grow to the size that that activity that we see predicts those central massive black holes are. So we don't know really how those 10 to the 9th solar mass black holes come to be in the first place, and then why that's tied to the growth of the galaxy bulge overall, we don't also understand. But that's why studying the black holes together with galaxy formation is so important, because we know there's a clear connection, and we don't know how either one really happens.
Oh, yeah, our viewers are very tricky questions sometimes.
Yes. No, good questions.
Thank you for the talk and for answering all of the questions. We will see you in the Zoom pub.
I will try to get to the Zoom pub.
Hopefully we will see you in the Zoom pub.
Okay. Thank you. Thanks for having me.
It was a pleasure.
Back to my old stomping grounds in Groningen.
Yes, Jake, do you take over to propose to people to join us in the pub? And
so please, everyone, come and join the Zoom pub. You can see the link on the screen now. And Stefi, I just sent it in your email, so you can.
Good. I was going to say, how do I find it? Okay, good. Thank you.
stem.oo/ZoomPub, and we'll be there very shortly with the quiz. We'll leave this running in the stream for a few more minutes so that people can get there. Thank you again, Stefi, for the talk. Thank you, Laurent, for hosting. And if you want to keep participating, we have the quiz, and you'll be able to hang out with Stefi and chat in our Zoom pub. So please go join it now. I'll leave the link here for about 30 more seconds before I have to go and join the Zoom pub myself. If you go join the Zoom pub, you will already get the code to join the quiz on Kahoot. So you can start joining the quiz right now, and we'll be there soon for the quiz.
It's just kahoot.it, right? And then the code, right? Yeah.
just kahoot.it, and then the code that Tice will give you in the Zoom pub. The only way to join is go to the Zoom pub. So this is enough time of us telling you that now. So please go join the Zoom pub, and our live stream will end now. But more than welcome to join us, participate in the quiz, or just chat while the quiz is happening, and then meet Stefi, ask her more questions, and join in with the conversation afterwards. Look forward to seeing you there.